Welcome. In this video, we will explore multi-level feedback queue scheduling, or MLFQ. It is considered one of the most powerful and flexible CPU scheduling algorithms used in operating systems because it can adapt to different types of processes automatically. Definition: multi-level feedback queue scheduling is an advanced algorithm where processes are allowed to move between multiple queues. Unlike simple multi-level queue scheduling, where each process is fixed to one queue, MLFQ adjusts the queue of a process based on its past behavior. This helps balance efficiency, fairness, and responsiveness. Key characteristics: processes can move between queues according to their execution history. Higher priority processes always run first. Preemption is allowed, so urgent tasks can interrupt less important ones. Features: multiple queues divides processes into levels of priority. Dynamic priorities: priority can increase or decrease depending on CPU use. Time slicing: each queue has its own time quantum for execution. Feedback mechanism: CPU-bound tasks gradually move to lower queues, while short tasks stay in higher queues. Starvation prevention: old or waiting processes get boosted back to higher priority after fixed intervals. Working: here's how it works. A new process enters the top priority queue. If it finishes within its time slice, it remains there. If not, it is moved to the next queue with a larger time slice. This continues until the process either completes or ends up in the lowest priority queue, which often follows first come first serve. Meanwhile, if a high-priority process arrives, it can immediately preempt lower ones. Advantages: very flexible and adaptive. Short processes finish quickly, reducing response time. Prevents starvation using boosting. Approximates shortest job first scheduling effectively. Disadvantages: complex to design and implement. Higher CPU overhead. Requires careful tuning of number of queues, time slices, and boost intervals. Problems and solutions: the biggest issue is starvation. A process stuck in a low-priority queue may never run if small tasks keep entering. The solution is priority boosting, which ensures all processes eventually get CPU time. Example: suppose a process needs 40 seconds, and the queues have time slices of 2, 7, 12, and 17 seconds. In Q1, it runs 2 seconds, then moves down. In Q2, it runs 7 seconds, then moves down. In Q3, it runs 12 seconds, then moves down. In Q4, it runs 17 seconds, then moves down. Finally, in Q5, it runs the last 2 seconds and completes. Conclusion: to sum up, MLFQ is powerful because it adapts dynamically, balances fairness, and prevents starvation. Though complex, it remains one of the most effective CPU scheduling methods in modern operating systems.